Hi everyone, welcome to our next video in the Week 2 series. Here we're starting Chapter 4 and we're discussing discrete probability distributions. Let's start with a note about notation. A random variable, which we introduced in Week 1, describes the outcomes of an experiment in words. The value of a random variable can vary with each trial of an experiment. Capital letters, specifically capital letters from the English alphabet, are used to represent random variables. Lowercase letters are used to represent the value of a random variable. So if capital X is a random variable, then capital X is written in words, and lowercase x is given as a number. You will notice in some other textbooks, they use capital X both for the random variable in words and for any number values that it can take on. So this notation is particular to the textbook that we are using. For an example, let's consider the experiment where we toss 3 fair coins. We're going to let our random variable x equal the number of heads you get when you toss 3 fair coins. So capital X equals the number of heads. We know if we toss a coin 3 times that each toss can be heads or tails. So our sample space has 8 items in it. Double checking that I counted that correctly. 8. We're making 3 choices, and each choice has 2 options, head or tails. So 2 times 2 times 2 is 8. So yes, that works. So then X, and this is going to sound tricky when we know our sample space has 8 items in it, can take on the values 0, 1, 2, and 3. And the reason X is limited to 0, 1, 2, and 3 is remember that capital X is counting the number of heads you get. And if you look at each of those items in our sample space, there's either no heads, 1 head, 2 heads, or 3 heads. So the numbers that X can take on are 0, 1, 2, and 3. Again, capital X is in words, and lowercase x is the number. You'll notice in this example, X values are countable outcomes. We're counting the number of heads. Because we can count those possible values, and X can take on the outcomes, that X can take on, sorry, words are hard, and the outcomes are random, X is a discrete random variable. And we've heard that word before. Discrete means countable. 1 person, 2 people, 3 people, 1 head, 2 heads, 3 heads. There are things that we count versus continuous, which are things that we measure. So this week we are focused on discrete random variables. So a discrete probability distribution function has 2 characteristics. Each probability is between 0 and 1 inclusive, and the sum of the probabilities is 1. And we know that these are 2 rules for how probabilities behave. So a discrete probability distribution function just follows the rules for probability for a given sample space. So for example, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Let X equal the number of times a patient rings the nurse during 12-hour shifts. For this exercise, X can take on the values 0, 1, 2, 3, 4, or 5. P of X equals the probability that X takes on value X. Why is this a discrete probability distribution function? So to answer that question, we're checking both requirements. Each probability is between 0 and 1, less than 1, bigger than 0, less than 1, bigger than 0, all the way down. All of these fractions are between 0 and 50 out of 50, which is 1. And then we check they add up to 1. So to check that, we check that the numerators add up to 50. So 4 plus 8 is 12, plus 16 is 28, 38, 42, 48, 50. So those do add up to 1. So this is a probability distribution because it meets these two requirements. We know that it's a discrete probability distribution because the X values are countable. A post-op patient can ring the nurse once, twice, 3 times, but not 2.5 times. Okay, so let's consider another example really quick. In this case, we want to suppose that Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days a week 15% of the time, and 1 day a week 4% of the time, and no day is 1%. Suppose 1 week is randomly selected. We want to, in part A, define that random variable x. Part B, we want to figure out what values that x can take on. And then in part C, we want to construct a probability distribution table. So let's go ahead and start with number 1. Let x equal the number of days. And if we go back to this problem, the second sentence gives us all of that information. She attends class 3 days, 2 days, 1 day, no days. So our random variable is counting the number of days that Nancy attends classes. Specifically, the number of classes she attends in a week. B asks us to figure out what values that takes on. And those are just the values mentioned in that sentence. 3, 2, 1, and 0. The last one is going to ask us to do a little math. It says, suppose 1 week is randomly chosen, construct a probability distribution table. We can see the table here has been labeled with 2 columns, x and p of x. Now we need to fill these values in. Now we already know from part B that x goes from 0 to 3. And the p of x values we can pull from the problem. So starting at the end of that second sentence, she attends no days 1% of the time, and 1% is 0.01. She attends 1 day 4% of the time. She attends 2 days 15% of the time, and 3 days 80% of the time. We're also asked, what does that p of x column sum to? And we know if this is a valid probability distribution, those probabilities should add to 1. So 0.01 plus 0.04 is 0.05. 0.05 plus 0.15 is 0.2. And 0.2 plus 0.8 is 1. So this does check out. Each probability is between 0 and 1. All of the probabilities add up to 1. So Nancy's class schedule and her attendance in classes per week does form a discrete probability distribution. Okay, if you have any questions, feel free to contact me. In the next video, we're going to continue this idea, but by talking about means and standard deviations for these types of distributions. I'll see you in the next video.